Alrighty. Today is the day. Let's see. I think this is probably my first solo solo stream here, so you're gonna have to bear with me as we go through this. But yeah, really excited to chat about this. I'm just gonna quote tweet that I'm starting. Started now. All right. So Vryx. So yeah, before we get started, I wanted to just do a quick overview of some other big news that we pushed out yesterday. So Kyle, maybe you want to start there. So after what was probably a year and a half of work around hooking up all the sort of messaging stuff that was originally planned for Avalanche, we yesterday released the pre-release code for what we're calling the Durango proposed upgrade on Avalanche, which will enable Avalanche warp messaging on the C chain and all the subnet EVMs. So if you haven't taken a look at that post, I'm just going to drop it here for folks to quickly take a look at. But this is a really huge change in stepwise function and how Avalanche operates and what it's capable of. And so, we're really excited to see what developers do with this, and definitely make sure you check it out. But with that, let's get to Vryx. So, where to start? Vryx is a lot. I guess it's one of those things when you get so deep into trying to work on a project that you forget how deep you got. And so I was, I wrote up the whole article, talked about what was going on. And then I shared it with some people, both internally and externally, saying hey, what do you think about this? And I don't think I realized some of the acronyms and things that I had just gotten so familiar with, just from reading so many papers and looking into so much stuff, that the write-up is pretty dense. And so I really wanted to host this live stream to just walk through it, start to finish, assume nothing about people listening or what their experience is with things, talk about where the ideas came from, some of the other ideas, other work people have done, and then where that takes us. So I'm super excited to go through this, and there's a famous quote where I didn't have enough time to make it simpler or shorter, I guess. I don't know who said that, but someone famous did at some point. That's the case here. So we're constantly, I'm trying to constantly distill the core ideas into simpler and simpler and shorter explanations of what's going on. So this is, I think, probably presentation 5 or 6 now. So it's gotten better since we started, but there's still some distilling to go. So it may be a little longer than I hope it will be eventually, but I think it's going to give you guys a good idea of what's going on here, assuming you listen to the whole thing. So cool. All right, Vryx. So Vryx is about fortifying decoupled state machine replication. So first off, why do we want to do this? What's going on? What precipitated this? That we wake up one day and say, let's fortify decoupled state machine replication? No. So all this started, I would say, with work on the HyperSDK. So while building the Hyp SDK, our goal from the beginning has been performance. So how do we get best in class throughput, best in class efficiency at that throughput? And so through that time, there's this first phase of actually building out the SDK, just getting it to work end to end, which is really important. But then as soon as that happens, your next thought, or at least our next thought for the HyperSDK, is, well, how many transactions can we actually process? Of varied complexity, whether that be smart contracts or whatever. And the core design of the HyperSDK was actually not that far afield initially from what we'll call traditional state machine replication. So state machine replication here is more of the academic term for what blockchains do, which is their state. You're trying to replicate that state to everybody and ensure that state stays consistent across state transitions, aka transaction processing. And so in the traditional state machine replication world, and I'll get back to this and talk about it a little bit more in depth, the whole idea is you got these nodes that collect transactions from random people. They put those transactions in blocks. While they're putting them in blocks, they make sure that they're valid. And then once the block is built, they send that out to the network, using maybe a more complex distribution scheme or whatever. But that's the core loop. And so you try to optimize that core loop, at least when you're taking your first pass at things, and distribute the block to the network, and try to get each part of that really, really fast, because your ability to maximize throughput is really how fast you can do that full loop across the network. And so initially, that was great, obviously running like these sort of high performance machines on like an extremely performant network hides much of the latency of the real world. So you see like people post these benchmarks all the time of like super high throughput, and it's, really great. Like you can go infinite if you have like your own, local network with max hardware usually, or something like that. But when you start to actually roll it out to a wide area network where you don't control the, communication lines, things change. Turns out there's bottlenecks in there that you really can't control. And some of those bottlenecks are physics with the speed of light and how quickly you can propagate data through a network. But as I started to play more around with these like max throughput experiments, what ended up happening was, and this is not originally my thought, but years of research people have put into this, is can you try and break apart these pieces of state machine replication to better improve the end-to-end time of the whole thing going on. So around Summit, I talked about this research deep dive I was doing, or really starting. So this is not an idea that popped up a month ago and it's like, oh, got it. Like I'll go write up something that's been on my mind for, I don't know, maybe 10 months or so. And so the first step in this direction was, when we're doing this loop of state machine replication, at least in Avalanche, in the way that we do consensus, you're not going to start voting on a block or building a next block until you've verified its parent. Or verified the block itself. And so with this loop, it can slow down, like the end-to-end confirmation time of everything, because I get a block, have to verify it. That may take a couple hundred milliseconds, and then I can start participating. So this is not my original idea, but when it applied to the Hyper SDK, there's this notion of trying to agree on like data and inputs rather than the results of that, or like the inputs and the results at the same time. So I started working on, different examples, different like kind of changes to the Hyper SDK code base to try and get this to work. But there was always this issue kind of in the middle, which is when you do this, how do you ensure that the data, like the inputs that you're actually agreeing to, are valid? Because you're relaxing a lot of constraints here, right? So like if I'm trying to just order data, like chunks of data signed by different people, you can do that. But in blockchains, a lot of the importance of like DOS resistance and everything comes from being able to ensure people pay fees. If I can just issue 1 million transactions and pay no fees for it, that's usually considered a pretty big issue. And so while I was playing around with this, there was this problem of, I need some way to track that I ensure that whatever transactions I include in the block can pay fees, so that I don't, basically just end up propagating and replicating a bunch of junk. I did some other stuff here where I was like kind of chunking up blocks into smaller pieces, because that helped. I could start like kind of replicating data sooner, but it's still at a high level, still retained this like broader state machine replication approach of, I'll take transactions in, I'll sequence them. I actually will start trying to replicate before I'm finished sequencing all transactions, but eventually get a block, and then that's the whole thing and send it out. So this was the impetus, and I was like, okay, this definitely makes it better. I did some experiments, and I was able to, increase the capacity of the Hyper SDK, but I still wasn't able to really max out the hardware of the machines. And there were these like really hairy questions around how you're actually tracking balances and how you can do that more generally. So put that in the back of my head, continued to work on productionizing the Hyper SDK, and then, made another kind of sprint up until the token wallet, which I think I released like kind of a GUI demo of things, which was my first real foray into like web development, getting this local wallet going maybe in October. And I started to do another pass at the throughput, and it was very unsatisfying what the throughput was. And I decided to take a step back and say, what if we just started over? Like, what is the craziest ideas people have in scaling blockchains right now? that aren't related to like ZK or optimistic stuff, but actually like L1 layer scaling. So that's where it makes sense to start Vryx. So Vryx, again, is about fortifying decoupled state machine replication. So decoupled state machine replication, for folks that haven't been following a lot of the recent literature and conferences, is really hot right now. Everyone is talking about, this is not a new idea. It was kind of rediscovered 5 or 6 years ago. There's a paper from Liskov and some other author from like the early 2000s talking about some of the core ideas here. So like many great ideas in, consensus research and state machine replication research, it came out a while ago and no one really, I think, appreciated some of the, novelty of the ideas, but it's really hot right now. And as a result, you'll see a lot of papers and a lot of also blockchain projects really exploring the idea. So what are they exploring or why? So as I mentioned before, we have this notion of traditional state machine replication. In traditional state machine replication, you have this, so as you'll see through this presentation, I've built these dummy models to help explain a point. Are they perfect? No, models never are. But I think they do a reasonable job of explaining what's going on. If people, if you have comments, the whole hack MD and write-up is everything is on my GitHub. You can propose some changes to it if you can think of a better way to abstract this. But the idea here is I want to show you why it's so hot. Like, what is the promise of this like kind of new way to do state machine replication, or AKA like blockchain processing, that's got so many people so interested? So let us assume that we have blocks just like we had before. And we'll call a block, for reasons that will be explained later, that they're 5 chunks. In most people's understanding of blockchain and blockchains you've probably used, you can just assume that those 5 chunks are really just one big chunk and they're just part of the block. You have this, then have this like sequence, execute, replicate step. And so in this example, we'll say that each build of a chunk takes 2 units of time. Each verification of a chunk takes 1 unit of time. Usually you can do that because you can better verify things or do more async. And then the replication takes 4 units per chunk. Again, models can be defined in an infinite number of ways. This is just the one that I think is fair and makes sense to me. In the case of build, this includes sequencing and execution for folks that are coming more from the state machine replication world. So in a simple traditional state machine replication model, let's process 2 blocks. And so the point here is we care about how long it takes to finish processing 2 blocks, because the time it takes end to end to process this, I can't build another block until I finish verifying its parent in the traditional state machine replication model. And so as a result, your throughput ends up being a function of how quickly you can complete this end-to-end loop of building, replicating, and then verifying a block across all hosts. There's obviously pipelining that can go on here that can help out, but usually, at least in the traditional state machine replication model, you can't build another block until you know the state of its parent. And usually you wait to do that until there's some finalization of the previous parent. But again, there's a case where this isn't true. The whole point is to say, what does doing things a little differently allow? So just grant me that this is a reasonable model for traditional state machine replication. So let's say that it takes 70 units between 2 validators. One builds the first block, second one verifies it, and then the second one builds a block and sends it back to the first one. The approach that I was talking about before, that I was like digging into the HyperSDK world on, was this notion of kind of splitting blocks apart into smaller pieces. Now, why would you do this? If you can see, this is a larger slide, so bear with me. You can start replicating the build before you finish building the whole block if you break it into chunks. Now, this lets the other nodes in the network begin to verify those blocks or block pieces sooner. What does that let you do? Well, that means, importantly, that validator can then build a new block sooner without actually relaxing the constraint at all, that all the transactions are valid in the block. Something we'll come back to called semantic validation. So that means that the transaction is valid and can pay fees. So what this lets you do is, if you look at where a traditional SMR was with the same workload, just with kind of moving the pieces around without changing any constraints, you can reduce the time by about 57%. Huge boost. So a lot of other blockchains are also doing this. And again, this idea was something that I think some people have done. I think, for example, Solana does this streaming approach where they like break apart. They basically start distributing the block as it's still being built. And so this, can lead to huge gains over traditional SMR. However, the core constraint here that I mentioned briefly remains. You're putting valid data in these chunks. So, you look at a Bitcoin block, there's no transaction in there that, mints the 22nd million Bitcoin, right? And you just skip it, right? That's not part of the block. You keep that all together. What if you were to relax that constraint? So let's just say that wasn't part of the story. You could just replicate transactions. You didn't have to care if they're valid or not, or traditionally valid and fully executable or pay fees. What could you do? So in this world, which we'll look at here, you could start building and replicating data before you had finished verifying its parent. You could also have people build and replicate data at the same time. You don't have to wait for them to actually look at what the parent is and then process that in order. So the paper that put this idea on a lot of people's radar was the Narwhal Tusk paper from the Diem folks a few years ago. And it really changed it reminded them of some of the things that were, probably not well discussed or covered from, 20 years or so ago, around really different ways you could do this. But someone listening might say, okay, cool. You can relax that constraint. And if that happens, you can do a bunch of stuff concurrently and end up being way faster in terms of doing end-to-end verification and building across a number of different blocks and validators. However, that constraint you relaxed seems to be a big trade-off. So you may, in the happy path, get way better performance, but what about transactions that that aren't valid, right? So the trade-off you're making is that semantic verification can't be performed prior to replication. If you look at this model, I don't know what the state of the parent is before I actually replicate the transactions in it. So, imagine you have a Bitcoin block, you have transactions 1 through 100. When you're including transaction 10, you can ensure that it's valid based on the state you have up to that point and the other transactions in the block. What if instead I said, hey, I'm going to send you these 10 transactions. I actually don't know the parents yet or what's included in them. But if they're valid, should be good. There's trade-offs. And so what the consequence of that is that the amount of fee-paying transactions per second can be much less than the replicated transactions per second. So what you actually end up replicating, because you can't actually fully verify those transactions at the time that they're replicated. So we call this notion invalid TPS. So invalid transactions per second, which basically means you've included data that may be syntactically valid. So the transaction may be correct, the signature may be correct, but it's not going to pay fees because the account doesn't have balance, or for whatever other reason, the transaction just can't be processed. And so a lot of research in the space so far has really focused on how do I use the metadata or artifacts that are created during this replication to really efficiently run consensus over that replicated data, so I can have zero overhead consensus, or really efficient consensus that relies on some of the data linking I do and how I replicate stuff or whatever. But when I was evaluating different ways the Hyp SDK could scale, what I found as I proposed many different ideas to Steven of different ideas, he's a great someone to work with. He offers really great insights and is really great at evaluating technical solutions. The problem is that a lot of them were great, but when we were talking about them, we were couldn't you just do this with transactions? Can you do this with transactions? And I found that most papers were not focused really on the quality of replication. They were focused on how do you really efficiently do consensus over these replicated artifacts, but I couldn't find a lot of information on how do you actually ensure that the replicated data is useful? Because if you're replicating gigabytes per second of data, but it's junk, I mean, what's the point? And so let's look into that. So what could an adversarial user cost effectively do? Could they increase invalid TPS? So this is transactions that can get validators to replicate, but that will never be executed or can't be executed for some reason. And examine at a high level, like theoretically, like what are the sort of attacks that people could do on that sort of thing? And Vryx, in a nutshell, is really about saying these are some like higher level theoretical approaches to make DSMR less efficient. Can we somehow introduce additional constraints into the replication and or execution stage to mitigate them? And I think so far, a lot of the research has focused on really treating the execution environment that's running on decoupled state machine replication as an independent variable, when the takeaway here is we believe it's a very correlated variable, and that it can't really be considered differently when you're thinking about replication and doing it in a decoupled way. And so, yeah, created another model here, which we call cool chain. And so parameterized it with a number of very specific parameters and rules to go over some interesting ways to interact with it. So the goal here was like, let's pretend I read a bunch of papers around like decoupled state machine replication. It was like, wow, this looks pretty cool. I'm not going to think about it too much, and I'm going to just put together like a little model based on, you know, first thoughts you might have if you read some of those papers or like think about, you know, really the benefit of decoupled state machine replication. So let's say that you have, you know, 100 validators. Each validator produces this chunk. So, you know, we talked about chunks before in blocks. Each chunk can contain 100 or 1,000 transactions. And for reasons you'll see later, let's just say that the validator limits how many transactions can be included per count per chunk, and that there's a delay of 2 chunks to understand chunk validity. So this is a very important parameter here. So when you create a chunk, like I said, you don't know the parent, and there's a process typically to actually get that chunk like attested to, or like that other people in the network will say, okay, if this is included, I can attest that I have it. Again, we'll talk about this a little bit more later. There's also great papers that talk about this, but this is needed for some security and data availability guarantees. And then to try and put a cost to these things, we'll talk about pretend that each transaction is pretty cheap. So a lot of these, I think, newer generation folks like are really, everyone obviously is trying to always get the price per transaction in blockchain down to make it more accessible to more people. And so let's just assume that Cool Chain has done that somehow. So other rules, you know, validators will listen to anyone over P2P. Like we don't want to try and give that up. So validators just ingest whatever transactions they hear. And if they think there's a chance that they'll pay fees, they'll try to include it. This is really important for censorship resistance. Validators can include any TX in a chunk. Like if they get a transaction, they'll try to include it if they think it pays fees. Validators purposely, if they see, you know, accounts with a nonce, they won't try to include that same nonce twice, just because they know obviously only one could be executed. Only one transaction per account per nonce can be executed. And then imagine you have these magic blocks that when they reference a chunk, all of a sudden it just becomes finalized. We don't care about the consensus part. In fact, Vryx ends up being pretty consensus agnostic. Let's just say that that somehow happens via some magic black box we have. So the first you know, way to think about this and like how efficiency can be attained or not attained here is around transaction duplication. So we'll introduce some notation here to kind of give you a better idea of like what this transaction looks like. So let's just say you have a transaction, its ID is, you know, in these brackets, or like transaction 0, transaction 1, it has some nonce and it does some action. If there's a star somewhere, that just means it doesn't matter. So in a simple model, let's just say that we have some account, me, and I decide to send, you know, I could get 1,000 transactions in every chunk. I'll send 1,000 of those transactions to validator 1, and then I'll send the same 1,000 transactions to validator 2, and I'll just complete that ad nauseum. If I do that, only one of the chunks from all the validators, doesn't matter how many, is going to get included on chain or like executed. So in this simple case, you know, you have this model where I can decrease what's called the fee paying transactions per second in this model to 1,000 instead of their original goal of 100,000, because we had 1,000 transactions per chunk, 1 chunk per second, 100 validators, which is a 99% reduction in fee paying transactions. And you can see with like the current fee parameterization, it doesn't get that expensive. Now, we're actually going to skip this attack because this has already been covered in literature a bit. I think the first one I saw that covered this was Mere BFT, which introduces this notion of transaction ID partitioning to get away from this problem. So, every validator is assigned some partition of TX IDs for some period of time. And so validator 2 here would say, oh, TX0, TX1, TX2 are not part of my partition. I'm not going to try to include them. Just going to drop it. Turns out there's other things that are in conjunction even end up being much more interesting than the duplication. So the first one is what we'll call conflicting transactions. So if you have nonces on transactions, you can issue transactions of different IDs that have the same nonce. So, let's say that I was submitting a transaction and then I wanted to increase the fee I was paying. Typically, I would issue the same transaction again and then just increase the fee it was paying. This would have a different transaction ID, but the same nonce. Because of our constraint that only one transaction can be included or executed with the same nonce, I can now send, imagine, 1,000 transactions to validator 1, and then different fee bumps to every other validator, but the same, another set of 1,000 transactions with the same nonces. Even if I partition based on transaction ID, it doesn't do anything for me. And I'm able to replicate the same efficiency of attack where I can decrease the max fee paid throughput by about 99%. So you may say, okay, 99% is pretty rough. Anything else you can do? Another attack that has to do with the delayed execution, which is a core part of all of these DSMR constructions where you don't know the state of the parent or don't know the sequencing of the transactions. So you don't know if someone will end up sequencing something ahead of you, is what we'll call fund exhaustion. So in fund exhaustion, let's say that I do the same thing as I was doing before, sending 1,000 transactions, but in the first transaction, I spend all my funds so that every subsequent transaction can't be executed because it can't pay fees. Because of the inclusion delay, so you get my transaction, you put it in a chunk, you wait for it to be executed, included in a block. You don't know for some period of time, am I getting more money? Am I losing money? How much money do I even have? And so if the first transaction, as the issuer, uniquely know because you're tracking what signatures you're signing and where you're sending them, you'll know that you'll spend all your funds and nothing else will be executed. So if you do this, based on the 4 transactions per account per chunk that we talked about, you can cause a 91% increase in throughput. This is not as effective, so it's much more expensive to run per day if you do this. But if let's just pretend like CoolChain didn't restrict how many transactions per account could be issued, you could really cause some reduction in throughput on the CoolChain if you did this. So you're like, okay, duplication seems reasonable fixes around partitioning inclusion. Conflicting transactions, a little bit more interesting. The same thing happens if you have UTXOs, by the way. You can treat UTXOs just like nonces. So it's not like specifically an account-based or a UTXO-based thing, but let's just say in this model that we care about account-based just to avoid mixing metaphors. And then, all right, like now if I send stuff out, I can fund exhaust. Well, things get even worse when you combine conflicting transactions and fund exhaustion. So if you could basically get away with, instead of having to always pay this first transaction, that you can only pay one of those first transactions. So in a model where there is no limit to how many transactions per account are issued per chunk, you can basically send one transaction out to one validator and then end up sending junk to everybody else and only have to pay fees for that one transaction. So the fee paying transactions can go down to basically 1 per 3 chunks. If you don't limit it, and then if you do limit it, you have to limit it to throughput divided by 4 in a sense. So so you can see that just taking DSMR, saying like, hey, let's throw it in an adversarial environment, what's the worst that could happen? If you're not careful, pretty annoying things can happen from people that don't have any control over stake just via issuance patterns. And so that's, one part of the problem. But the other half is, great, let's say that someone did this attack or any number of these attacks. You end up typically persisting those chunks because they contain a mix of valid and invalid transactions that anyone performing a full archival sync or trying to actually verify the hash of things included in blocks would have to go fetch. So you end up indefinitely persisting these massive transactions, especially or useless transactions, especially if the consensus is connected into them somehow, or into the chunks where you still have to fetch them and the hashes are part of actually performing consensus down this chain. So the cool chain nodes following this attack are basically just storing, terabytes of stuff that's entirely useless, and they have to keep it around. And let's just say even more so, but let's take a step back. Cool chain, before they decide to start doing all this replication, they decide, hey, let's say before someone even considers trying to do these attacks on a decoupled state machine replication, they say, maybe the fees, the transactions are getting saturated, cool chain's doing really great. They have, 100,000 TPS, and they're trying to introduce some sort of feedback pressure to keep the system stable because it's, processing at capacity. They don't want people to start fighting over the network layer to try and get transactions included. And so they say, hey, we're going to introduce dynamic fees, and we're going to base those fees off the number of transactions that are included that actually pay fees. So, 100 based on the number of valid transactions. If you didn't do that, right, any validator could just stuff junk in the block and then drive the fees down. So we're cool chain devs decided, the best way to do this is just based on valid transactions. Well, little do they know, in this model where you can kind of cause all this deferred execution and where there's deferred execution, we don't know if the transactions are valid. If you perform these attacks, you actually, by doing so, incentivize the attack, because developers maybe that were used to paying the base fee at 50,000 TPS or something like that now have to pay more. But they realize, hey, if I start to replicate a bunch of junk, I can actually drive the fees down. So I may want that, and I don't really care about the global throughput of the system. I care about me. So I'm going to just start doing that, and as a result, fees can drop. Obviously, this is all dependent on the fee model that the cool chain devs use, but you can see how you can incentivize an attack if the fee parameterization is based on basically fee-paying transactions, which for a lot of reasons would make sense that you would do that. So that's a lot. The question becomes, how do we get this without having to have this? And Vryx is all about that core question. How can we take advantage of the best of DSMR? It's not new ideas in DSMR per se, but how do we constrain DSMR better such that we can avoid this situation, which only requires adversarial users to have access to a chain with this type of model. And so Vryx is all about saying, well, there's a lot of things you can and can't do when you don't have semantic validation or verification on chain. You can't, if you really want to take advantage of DSMR, you're not going to have the state available at the parent unless you really slow things down, and you eventually start to look a lot like the streaming SMR like we talked about, where you look at the parent state. So assuming we don't want to do that, we're not going to have anything deterministic we can utilize to verify these transactions. We need to use heuristics. And so the question becomes, well, if you have heuristics, they're not enforceable. The only people that will follow them are profit maximizing folks. So if that matters, well, maybe we can put something together, some sort of framework, some sort of collection of constraints that allow people that care about not sequencing junk to minimize or hopefully get to zero the number of invalid transactions per second that they replicate and then eventually sequence and execute. We can't get rid of the entire problem of having to verify junk or store junk temporarily, maybe, but at least if most people are honest or profit maximizing, we should be able to hopefully drive this number down by giving builders of these chunks more tools to control what they include and ensure that there's a higher probability that they end up paying fees. So Vryx is more or less 3 or 4 ideas when coupled together end up, in my opinion, introducing a much more difficult environment for adversarial users to game and include replicated transactions in. And then for anyone that's actually deploying a system that is using decoupled state machine replication, should make it more robust in the case where you have adversarial users present. There's some things that I do in the Hyp SDK construction of Vryx that I think could improve throughput in the happy path. But the focus of this is saying, the even average path of decoupled state machine replication is pretty darn good. Like if we can just get to that, we should be pretty happy. So the cool things I'll call out here, first of all, is the name is awesome. But secondly, because Vryx really deals more with constraints around replication and execution, it's pretty consensus agnostic. All you need to be able to know is like basically have validators or block producers or chunk producers that have access to the validator set, and then also have at a particular height, and then also have some notion of like a cryptographic identity, which I think almost every proof of stake blockchain, that's already part of the story. So, and then as a result, you can pair it with your favorite decoupled SMR. So let's go into these. They sound cool, fraud proofs, right? Everyone loves fraud proofs. So first off, temporal account partitioning, or actually, I think I have the order of these wrong. I'll come back to that one. So let's think about our failure case here. So we have accounts that can end up spending all their funds. You don't know what their funds are at any point in time, so you can't really protect against it. Let's start there. So Vryx first suggests including this notion of an account fraud proof and an account bond. So the idea would be when an account is created, you end up locking up some amount of funds in a bond that can't be accessed or deducted on during the entirety of the existence of the account, such that if I choose to issue a transaction that spends my balance down past zero, any builders that include those transactions would be able to then deduct the fees that you owe from that bond. Now, why can't you just do this at some scale? Well, you want that bond to be as small as possible. So like, if I wanted to go issue transactions on chain, I'm not going to go lock up $10,000 to issue 2 transactions. I need a smaller amount here that I can, otherwise it becomes prohibitively expensive to use. And so in this world, if a transaction is included that actually overspends a balance, we could call that like a fraud proving transaction, where you can clearly say during execution when you have state that you're spending funds that you don't have, and at which point validators or whoever included your transaction can now deduct that bond. Now, this comes back to then, what are the things you can and can't do when you don't have full semantic verification? Validators, importantly, can track how many pending transactions that they have out, or like that are from a particular account, and what the bond balance of that account is, to ensure that they don't include more transactions than the transaction fees they could claim. No one can enforce this other than the chunk, or like the builder that actually includes transactions from that account. So it's not something anyone else can enforce, but a heuristic that the builders must follow if they want to maximize their profit. But the issue now becomes, well, Patrick, before in the cool chain model, you said I can issue transactions anywhere. Well, if I can issue transactions anywhere, then this bond has to be the size of the account, like a function of the size of the validator set. Otherwise, I have no idea, who has what transactions and who's sequenced what. Like my only mechanism for communication is these chunks that don't know the state that they're included with. So that's where we get into account partitioning. So the idea here is not only think about transaction partitioning, but actually partitioning accounts to particular validators, configurable based on the amount of censorship resistance that a chain or whoever's employing this construction wants, where you basically make the bond size a function of the number of partitions that are valid for a particular account. And so you ensure that everyone always has enough to claim their fees, and then the number of transactions that they're willing to keep outstanding is a function of the amount of fees that they can claim. Now, you may say, interesting, you have these bonds, right? But how do I end up, really keeping track of things if accounts have nonces and, there's like, if I send the same nonce to two people, great, they're both I'm both validly partitioned, but they're going to include both of those transactions because technically that's valid. So the next step is including nonceless transactions. So the third mechanism that's included in the Vryx constraints is no nonces. So what this allows is you to have non-dependent transactions to be issued within your partition, so that you don't have to say, oh, I sent nonce 3 to this issuer, nonce 4 to that issuer. If nonce 4, or if like the issuer that gets nonce 4 includes the transaction first, nonce 3, or includes it before nonce 3 is included, then 4 can't be issued. It becomes a trivial attack to then like send all these out of order nonces all over the place, and none of them will be executed. So in my opinion, to avoid the data dependency problems there, you just have to drop the nonces entirely, unless you want to have accounts assigned to a single issuer or builder. But even if you do that, you end up having to wait for this execution delay. If you were to do that, where you would have to wait for your node to catch up to the latest state to know if the transactions that are being included, have some sort of like included or not by the time you actually end up issuing them, and other validators stop being able to include for that particular account. And so that's not great, but if you get around that and instead use like expiry windows with nonceless transactions, you can actually overlay these windows so that there is no pause in throughput. Now, this is a little bit more of a nuanced topic. I'd recommend checking out the write-up if you're curious about what I mean there. The other thing that's really important, I guess like a lot of the ideas around Vryx unrelated to fortification are around trying to minimize data dependencies of these like decoupled state machine replication blobs. And for that, there's no nonces and there's no, and we use this like TXID thing, and there's expiry windows. So data, if it eventually doesn't get replicated or whatever, it just disappears. So you don't have this hangover of trying to deal with data that was previously replicated or issued or somehow just never got executed, that you need to include and fetch somehow to go process future data. And so everything has expiries, so that if there's like some sort of instability or something happens, that data just disappears and can be reissued at a later point in time. But the system itself doesn't have to pay the price for having to organize that. Whoever's issuing data would just start over. The last one has to do with that aftermath question of, I'm holding all this data. I can't guarantee that people are actually going to follow these heuristics. Can I do anything about it? Yeah, you can. So there's a zero communication overhead transformation you can do, where you take raw chunks and then you basically create filtered chunks out of the raw chunks. And then everyone can deterministically generate the hashes of the filtered chunks and then include those in blocks, so that future people that are actually coming to come sync the chain, or just on the validators themselves, what they actually have to serve is only fee-paying transactions. So this is a nice transformation you can kind of do, not too complicated at all, frankly, that can transform these chunks that may include a bunch of invalid transactions into fully filtered transactions. So this ensures that the weight of any sort of malicious or like not profit-seeking what I think would be called like a non-compliant block producer doesn't impact the stability or efficiency of the system. So what this ends up looking on the Hyp SDK is we got a few adaptations to the core ideas here. So I'll pause for a second. A lot of the future work, in my opinion, into this is trying to be more formal about the issues that you can run into in decoupled state machine replication, and trying to prove what type of constraints are required to actually enforce this. I think some of these ones are definitely more cumbersome constraints that seem to solve the problem when we look at like how they actually address the issues from previous, which the write-up does a good job of going into. But in terms of whether or not they're minimal or like somehow describing in closed form like that they are minimal, I think is future work to do, and something that I'd be really interested to work with a collaborator on to try and come to that. But we are now in the stage of taking these Vryx constraints and now bringing them into the HyperSDK to hopefully increase the throughput to a much higher level than we're able to get with traditional state machine replication or streaming state machine replication. And so the way that this construction works is you have HyperSDK blocks that have this deferred reference system. So the idea is that the blocks themselves actually run Snowman consensus, which is the standard for any subnet. But the blocks themselves actually include references to chunks that are distributed outside of that consensus mechanism. Now, there's one small nuance here, which I'll include, and I'll go into some of the specific data structures. But blocks actually reference the certificate of chunks, like of properly replicated chunks prior to their execution, so that anyone that sees a certificate for a chunk can go fetch it, even if they didn't have it received. And this deals with this issue where if you were forced to execute a chunk exactly when it was referenced, you may have to go fetch it. And if you're the next one that's supposed to build a block, that will cause the whole chain to get stuck, or you to build on an orphan or something like that. So it's very important to reference data before you need it. And then you can parameterize how long of a gap there is from the time of reference to where execution is required. Now, a really nice byproduct of that is that execution, you can do all sorts of crazy tricks there because it's just asynchronously done and then required at a later point in time. So you can spawn that off to some massive, compute farm if you wanted to, some crazy databases somewhere, like batch things together in some cool way. But the important part here, which retains the original ideas from like replication, are we can actually agree on the data before we know the result. And when you do that, you can make things much better pipelined. Hopefully, increase the throughput of actual execution. And so I talk in detail about how this works inside of the write-up, like I said. But now I'm going to go over a few small data structures that are utilized here. So you create these chunks. Chunks have producers, they have some expiry, and then some beneficiary for like the fees that are collected. Note that chunks don't have any ordering dependency whatsoever. A chunk from a single validator could be included after a previously replicated chunk or before a previously replicated chunk, because the transactions have no dependency order. So what that allows you to do is like you can just get away from all these edge cases and issues of having to go like fetch long runs of chunks or something like that to go like include the next chunk or whatever. There's no data dependencies here, which means that you can just include whatever you have whenever it's ready, which really helps, in my opinion, keep the system stable when you have random network faults. Blocks, like I said, include available chunks. And then some number of configurable blocks later will include the executed chunks. Now, the executed chunk ID is actually the filtered chunk hash of the available chunks ordered from N or K blocks ago. And so you then only retain the executed chunks here, and then you can just prune after some number of blocks all the original chunks, which are no longer going to be available to anyone on the network. Because everything, obviously, too, just like any system that does this, has like IDs that are deterministic, and the chunks themselves aren't that big. You can just have nodes that just say, hey, you want to sync this chunk? Go to this external data store and fetch it. This is its ID. I'm not going to give it to you. Because validators here, ideally, are only doing work to proceed in consensus and move and finalize new transactions. But trying to keep them also being the one that serves like infinite amounts of data using their like extremely precious bandwidth, not the most scalable thing you should do. So it should be possible to reference these chunks more externally that then people can go fetch. And so what this ends up looking like on an end-to-end transaction lifecycle is I'm a user. I submit my transaction to some API node. I can do it to a validator directly if I wanted to, but let's just say I submit it to an API node. That API node then forwards it on my behalf to the validator that I'm currently partitioned to. if my bond or my account's not frozen, like I have a valid bond and like I didn't fail to like issue a transaction in the past, they'll then replicate it in a chunk, and then they'll wait for that chunk to get some percentage of stake weight on it to be signed to have a valid certificate. There's a game here a bit where like you don't really want to require more than 66% plus 1 of stake weight on a chunk for it to be valid, but you do want to encourage broad dissemination of the chunk. And so in Vryx, at least in the HyperSDK setting, we pay a fee, or the percentage of fee you get for replicating the chunk is actually a function of the stake weight on it. So there's some game theory there about like, if you get 66% plus 1, you can send it, but you're not going to get all the fees. You probably want to wait till you have like 90%, 95% of the stake weight and then send it. And then if there's some validator that's just not giving you signatures, like, well, just don't sign theirs. And you can have this like tit for tat penalty for not helping each other out. But it doesn't impact the stability of the system, because you can still include, if no one else is online, 66% plus 1 of that chunk. Get the chunks back, you reference them in the block, eventually they're executed, and then you send back the transaction status to the user. So one other point I forgot to mention, at least on the fraud proof side, is you could instead require having some like sort of data availability account where like you're paying for inclusion separately than execution. But the issue if you do that is that you have to keep topping up that balance. And that's what originally I was thinking about doing in the HyperSDK original, like agree on inputs, not execution setting. But the issue is just that it's such a terrible UX. So even though account fraud proofs is by no means the perfect UX, I felt it was much better than having to continuously like top up your account, especially if, I don't know, you forget to do it, you run out of funds. Now your account's stuck until you go get more funds or something to top it off. So yeah, that's it. Only took 55 minutes to get through this presentation. So in the past, I've tried to give this presentation in 25 minutes, and at IC3, I tried to give it in 8 minutes. You can imagine how that went in terms of understanding. So I was really glad I was able to make it through in the hour, I guess. That's good to know that that's about how long it takes. So yeah. So that's that. I collected a number of questions people asked about Vryx on Twitter and different areas that, we have 5 or so minutes left here that I'm going to try and run through. So give me a second while I pull those up. So the first one someone asked, I think their name on Twitter is Sam Laffer. I don't know if you can see this, Kyle. Maybe not. I'm just going to go full zoom in mode here. All right. So at the cost of latency, why does everyone keep forgetting about latency? Let's remind ourselves what latency is. So the question, fair put, is what are the trade-offs of doing this, right? Like we talk about throughput being important, but we don't, in this process, or like the analysis of decoupled state machine replication, or at least even Vryx, talk about what the end-to-end latency of transaction inclusion is in this system. So if we go back to the one that we're considering for the HyperSDK, right? You have a transaction, or actually I'll go to the lifecycle. You have a transaction, you send it to an API node. That API node then forwards that to a validator, or you could forward it to a validator. Then they include in a chunk. Then they get, there's a lot of round trips here. Get the chunk signed, bring it back. And then execute the chunk after people have enough time to go actually get it. So if you want like full finality from the system of actually having like on-chain execution of the results, in the worst case, it may take a few blocks to finalize a transaction. Now, in the happy path, though, very much not likely, right? There's 3 phases of confirmations you can give people. So the first confirmation you can give people is it's included in some chunk, which is only going to take 1 round trip. Now, if it's valid transaction fee paying, you at least know that it's probably going to get included in a block with, I don't like in the happy path, we'd have to, run some data and see how likely that is to happen. But you can have that notion without actually having full confirmation. And if it's a simple transaction, you know that it is most likely, you could probably even reflect the balance of like a simple transfer as soon as you have a replication certificate, if you know it's a valid transaction. Now, if it's not a valid transaction, obviously, you're going to get your bond taken away, your account's going to get frozen, all this other stuff that goes on. So let's just talk about the happy path case of different optimizations you can represent the results before that. The second one is, let's say, it's a more complex transaction, like a smart contract interaction or something where you don't know the outcome. Well, if you actually have all the certificates that are referenced in blocks, you can execute them immediately. You don't have to wait for the execution deadline on chain. So assuming that happens and the chunks certificates are referenced and you have all the chunks, you basically just wait for the chunks to be included, which 1 round trip, and then chunk certificate back sent to some block producer, 2 round trips. As soon as that block is referenced to you or you see it, which would probably be like the 3rd round trip, you could then just execute ahead of time, which shouldn't take more than a couple hundred milliseconds to process transactions. So in that world, if you have the data, you can actually proceed much faster than the worst case that the chain is trying to support here. But in the worst case model, let's say everything's shit, people are referencing certificates that you've never heard of, you got to go fetch them, you got to do whatever, and no one's giving them to you, you got to wait the full time to go get it. Then it can take quite a bit of time. But I would argue in that world, a traditional state machine replication model is not going to be perfect at that either, because you may try to replicate things through the mempool, people may not sequence. And the idea there is that if you have increased robust scale, that at least at the state that blockchain's at with the number of users that use it, it should be more than sufficient, hopefully, to ensure that most transactions that are replicated pretty quickly would be the goal. Another person, I think Devin, asked a question. So how does this compare and contrast with like what folks are doing with other virtual machines? So like a lot of attention is going into like Monad, some of these other EVM chains, Solana rollups, CK rollups, unrelated really. So like I think a lot of energy right now is going into like execution parallelization, which is something the HyperSDK already does. This is much more about how do you efficiently replicate that data to as many of these like participants as possible, and from within that do whatever. But just simple transaction parallelization addresses nothing related to like the efficiency of like the data replicated in DSMR, or is even necessarily maybe related to DSMR. Anyone that's just verifying execution after sequencing will have the same problems that I think are outlined by the cool chain model, but the degree will vary based on the type of construction and constraints that there are. And this is the important part of actually outlining a well-defined model, which admittedly I think could be done better on in the Vryx write-up. Is that all of these things depend on the constraints that are in place. Like I don't know what constraints other folks are using. And I think everything's always growing and changing in the space. So it's important when you're presenting an idea to use a well-defined model to base those ideas off of. So I got another set of questions here. I know we're actually probably over time, but I wanted to get to 1 or 2 of these. Quick questions I got. Does Vryx only support payments, like smart contract interactions? Can that be included? Yes. So the whole point was to make Vryx as generic as possible for the execution layer. So as long as whatever the execution layer is can provide, account fraud proofs, it doesn't understand whatever else you're doing. You can support any interaction you want. So like if you have a transaction that says, hey, like I'm the issuer, I know I'm going to spend all my funds, go send it. Well, that you're calling a transaction that can do that. Obviously, whatever DSMR system here can't do that generically. So you have to penalize that person, but it doesn't require you to have knowledge of like simple transaction types or anything like that. So it's should hopefully support generic, transaction execution. And one thing, and I know this is the last one I'm going to answer because I think I do spend some time actually going into it in the write-up. Is a lot of attention these days is focused. Let me go zoom in here on account abstraction and ensuring that like the systems that we're working on can support that. I also thought a lot about like whether or not Vryx, like the constraints in Vryx, ended up being compatible with that, and there's some nuance here. So because we need anything that's included in a block or a chunk by like a profit maximizing producer to hopefully be verifiable, it's important that the mechanism that's used to actually verify the authentication for a transaction can't be revoked or modified from the time that a issuer includes or a builder includes a transaction in a chunk to the time that it's actually executed. Otherwise, like, throw the profit maximizing goals out the window. Like, I'm just going to start like swapping my signing key on my like account, constantly to avoid having to pay any fees. So you can't get rid of that. However, using like the partition framework we had before, and there's like definitely some synchrony assumptions here. You can say, hey, great, you can change your account signer, but it's not going to take effect until some sort of configurable constraint on like my ability to read the state. So I can say, hey, yeah, like I'm going to schedule a change to my signing key or something like that. And it may not take effect now, but if you wait 2 epochs, which may be, 5 minutes or probably far less, maybe 3 minutes or something like that, then your new signing key will take effect. And so there is compatibility. You just have to be very careful around ensuring that transactions have non-revocable authentication verification. And that in the case where you do want to modify it, you can ensure that profit maximizing producers can read some form of state by some time to ensure that they're like checking the right authentication constraint. So it's possible. I actually was playing around with some demos of this a few days ago on the Hyp SDK, but just wanted to clarify that should be possible still with this model, with some constraints again on exactly what is going on here. Like the account abstraction should not be able to just read arbitrary state, but if you, let's say, had use this ECDSA signature to verify this, and you want to swap that ECDSA signature, that should be very possible. So it should be compatible, but as with many things in blockchain, it's always a little bit more complicated than it seems when you take a look at it. But yeah, thanks everyone for stopping by. I'm really excited to continue chatting about Vryx with folks. I'm working on implementing it now in the HyperSDK. And look forward to listening more to people's ideas. And, I'm sure that there's a lot of ways to extend this and good ideas of how to make it even better or more efficient, and look forward to chatting people with that. So thanks for taking the time. And yeah, thanks.